right, let's get started. So we're actually going to continue where we left off from last lecture, talking about creating our own objects. Do I need to adjust the screen? Okay. All right, and does this do a thing? Yes, it does do a thing. So last class we talked about creating our own class implementations. A class describes a physical, real-world object, describes its properties and its behaviors. Okay, we talked about fields versus properties. Behaviors are methods. Today we're talking about structures. Structures are very similar to classes with a few important differences. They are a primitive data type. They are represented using the keyword struct. So instead of using the keyword class, we use struct. They can have properties, methods, fields, and constructors. They're mostly used for data, as opposed to things that have a ton of methods, actions that they can perform. It's for storing large amounts of data. So we call them structured data types or abstract data types. On the whole, they look like classes, but they're called structs. So we have the keyword struct, the name of the structure, in this case a point. We define two properties. These properties are auto-generated properties. What's the difference between an auto-generated property and a non-auto-generated property from last class? Yeah. You're thinking of static methods and static variables. A auto-generated property does not have a field associated with it. So this just says public int x get set. That get set is the automated generation. When we create our own properties, they have a field behind them. So we're controlling access to a field through a property. This property auto-generates its own field. It's hidden away. Same with the struct color. All of these are public properties so that anybody can use them. In this example, we expand on this a bit more. Specifically, we provide a constructor. When we provide this constructor, the keyword this refers to the parameterless constructor. Anytime you're inside of a class implementation or a method, this keyword corresponds to the object you're running the code as. We saw last time that there were 3 dogs. They each said bow, but the things that were printed were different because each method call operated on different data. Okay, so formatting errors aside, I'm not sure what happens between here and my office, but generic classes and methods. This is usually the hardest thing to visualize at first glance. A generic class is a class that doesn't actually define a single type. We've made classes that define the type dog or animal. That's a single type. Generic classes allow generic data. Okay. We've seen generic classes already. When I did the lecture on arrays, we did arrays, which are statically allocated, and lists, which are dynamically allocated. This is an example of a generic class that already exists. The generic part is this T. When you say list of T, that T can be any pre-existing type. So now that we have, last class we made a dog class, we could have made a list of dogs, a list of students. Okay. In C++, they call them templates, templated classes. Okay. In Java, I guess they call them generics, but we're not in the CIS department, so we won't deal with that. Create your own generic class. You see this mostly in container classes that contain other data types, but all you need to do is, in addition to providing the name of the class, put the braces and T. It can be Bob, it can be Joe. Generally, we just say T. T is a stand-in for whatever type you're going to create. So everything that you do inside of the class is in reference to some unknown type that will be declared later called T. So here we have a generic class which defines one method called add. That method, when we, I can't point at the screen, I've got to point up here. When we create our generic list, we give it a type. So this int is going to appear in the method implementation anytime you say T. So when I say add key element, when I create this generic list, every place I see T, it's going to be int. When I say generic list string, any place I see T up top, it's going to say string. So when you create a string list, if you say string list.add, it will expect a string. If you say int list.add, it will expect an int. That's it. Okay. The under the hood details, every time you instantiate a generic list with a type, it creates a new template that actually replaces all of those T's with string. So it's actually creating two different classes, one for each instantiation. Okay, if you instantiate this using other types, it will create a third copy or a fourth copy. Let me head over. I want to be able to do constructors, generic classes. Come on. And to show that to you, do that, and project. So, what? Better. Okay. So here is a CS file, a C# file, that is defining just the class that I care about. In this case, it's called generic list. This is a bigger version of what was in the slides. It has one generic parameter called T. That's going to be a stand-in for a type. The first thing I do is the class declares an array of elements of type T. So T isn't a type that exists. It's a stand-in. So it's private, meaning that no one outside the class can access this array. I also declare a private variable called count, which I start at 0. This method right here has no return type. Furthermore, its name is the same as the class name. What do you call this kind of method? Abe, you made eye contact, man. You should know better. What is it called when a method is the same as the class name and has no return type? A constructor. It's a special kind of method. Its job is to initialize all of the internal state. Of course you did. You told me. Why would you tell me twice? It's better the second time. All right. Like this class. What is the internal state of a generic class? It's defined on the screen, but what does it mean to say the internal state? Say it louder. Specifically variables or fields inside the scope of the class. The scope of the class defines two variables, two fields. So count automatically gets assigned 0. That's fine. That's inline initialization. That actually happens before the call to the constructor, but after it's been initialized. So the only thing we need to make sure we have initialized is this thing, elements. Elements starts off as a reference type. So inside the constructor, we create a new array of type T. What is T as a type? It's a type. What kind of variable does it hold? No. Whatever we want is an answer I accept. You could have named any type that exists, and I would have told you you were wrong, because it will hold whatever you tell it to hold. T is a stand-in. It's gonna, you can think of it as a find and replace. Okay? So T is just some type that we define, and we define it inside those braces. Okay? So what is this thing doing? It's really just creating something that is like the list class already. We've got a count. It's a read-only property, and it's just a stand-in for the count variable. This method is more interesting. Okay, this method takes one argument of type T. T is just a stand-in for whatever we have. It could be int, it could be float, it could be string, it could be dog, it could be room, doesn't matter. It's based on how we allocated this object. So what do we do here? We take in an element, and if there is space left in the array, we put it in and we update the count. If it's not, what is this? What's this line here going to do? Yeah. It's going to throw an exception. In this case, index out of range, and it's going to give us a little bit of a message. The list capacity of blank was exceeded. Okay, so this is an example of code that knows that something bad could happen, but is not going to try and fix it. It's just going to throw an exception, let someone else deal with it. Let the calling function, whoever called add, is going to have to catch this index out of range exception. Yes? When you make the constructor, it is of type, where am I? Of type T. Count is the number of items in the list. Yeah, it's an int.
What about the constructor there, the public generic list int capacity?
So how do you allocate an array? You give it the type, and then the size of the array goes in the square brackets. So this is allocating capacity T's. So if capacity was 10, it'd be allocating 10 items of type T. Okay? All right. This one is fun. No pun intended. This is a new type of function. A method that we have not talked about, although I mentioned it. I mentioned something last class called an indexer. This is how you declare an indexer. When you access arrays using square brackets, this is how it's implemented. Public, because anybody should be able to call this. It's going to return an element of type T. How do you call it? Directly based on the name of the object. So if I created something called my generic list, I would say my generic list, open bracket, 5, close bracket. So it takes in an int. Inside it's read-only. We don't have a write property here. And what are we doing? Again, we're checking to make sure we're not out of range. We probably should check more than this, though. What else could be passed in as an int that would cause this program to blow up? A negative number. Okay. So we only check to make sure that index Did it just go to sleep? Still recording? Still recording. Where do you define what T is? Outside of this file. Let me just, this is the end of it. So all it does is you can add and access. That's it. There is another file in this project, the example file. So part of encapsulating your code, separating it out from the user, is we generally keep one file per class. So if you have multiple classes, you'll store them in their own files. So here is the actual program. You can tell it's the main program because it has the function main. Here is where we define what T is. When we instantiate a variable. Generic list was the name of my class. It's going to call the generic list constructor. But specifically, we've got a generic list of ints. And that's how you would read this, a generic list of ints. So you can think of those braces as of. So a generic list of ints called int list, and this calls a parameter list constructor. We don't give it a parameter. Now the parameterized constructor said the size was an argument. Let's go back in there for a second. Let's find the parameterless constructor. Here it is. I missed it. It was so tiny. A parameterless constructor, or the default constructor, those are two names for the same thing, does this, colon, this, open parenthesis, default capacity, close parenthesis. That is shorthand for call the parameterized constructor. The parameterized constructor takes a capacity. So what is default capacity? It's that constant, 4096. So that's picked up at random in this example. So what is this actually doing? This line calls the parameterless constructor, which in turn calls the parameterized constructor with 4096 as a size. The regular constructor then allocates an array of ints, 4096 ints. So it's already allocated, we've got it, it's on the heap. An int list is a reference to the generic list. The generic list has a reference to the heap. So add 1, 2, and 3. We access the int list number of elements by saying .count. And then we use the indexer. So this is calling the indexer method. The indexer is just the first type of special purpose method. There are other methods for overloading the plus operator, overloading the multiply operator, and so forth. But this is an indexer. Okay, it's how you access the index of an array. And what is it doing? It's grabbing out an int and printing it. The description of the code is actually much more interesting than the actual running of the code. It's going to print out 1, 2, 3. Yes? I think you would, because it's a type-checked language, bad things would happen. So what happened here? Oh, so this was the second one. The second part of the example gave a capacity of 3, but then tried to put 4 elements in. Okay, and that fourth element caused an exception. And the exception is exactly what you'd expect. The list capacity of 3 was exceeded. It was inside, and this is how, can you read that? Can I make the font a little bigger on this? I think it's important that you read what just got printed. Okay. It says generic apostrophe 1 dot add T element. Okay. That is code for it's a generic. Okay, the generic list dash 1. Okay, if we were to do the same change here, parameterize that to be of size 2, so that will cause it to create an error. So this should not run, it should throw an exception. Okay? We still get the error message, but again, it says '1. So when you see apostrophes in there, that's a good chance you're looking at some kind of generic. The other giveaway is the fact that it says T element. Okay. There might be. I don't run into this kind of error a lot. Yes? We can try it out. My belief is that these arrays are bounds checked, but I don't know that for certain. But we can take the check out and try it. Okay, we just will get I believe what will happen is we'll get a less informative error message. Yeah. So same place inside the add method, specifically line 36. Okay, oh, line 36. So it's on this line as opposed to the line up here that we threw it from. Okay. And it's even the same type of error, right? Index out of bounds. Index out of range. Yeah. So we threw an error that already would have existed, but it's a good example of how to do array bounds checking. So now I've got to switch back to, nope. Yep. Yep. Nope. Oh, I know this one. Close. There it goes. Okay. And now I got to get back to my side. Okay. So generic classes can be powerful, especially if you want to augment the abilities of an existing list. Okay. So that's all that I wanted to finish up on that slide, or that set of slides. So we're now going to skip all the way ahead to chapter 20. Okay, we just finished like chapter 14 is classes. But now I want to talk about some more properties of object-oriented programming. Okay, now that we know how to create our own classes, there are several rabbit holes that we can explore. Each one of these keywords is going to show up on a job application one day. Okay, inheritance, abstraction, encapsulation, polymorphism, those are going to show up. Cohesion and coupling are what's going to allow you to keep the job if you get it. Okay, these are best practices for programming. So let's talk about these couple of vocab words here. The idea of inheritance, we've actually talked about this before. There was another time where I showed this sort of hierarchical graph. Does anybody remember what that graph was of? Exceptions. Okay. I tried to avoid using the word inheritance at the time, but now it's time to talk about inheritance. What does inheritance mean? Aside from an interesting book by Christopher Paolini. Yes? No. Forget classes. Like the word, dictionary. Forget like... Something that you pass down. You get an inheritance from your forebearers. Okay? And inheritance just means you're passing something to something else. In this case, in the concept of coding, inheritance means that you are giving your descendants all of your fields, all of your methods. So, classes can inherit from one another. Now, all dandelions are plants. Dandelion is a type of plant. All salamanders are animals. They're a type of animals, a type of animal. Okay, armadillos are a type of animal. So if we create a class called salamander and a class called armadillo, there are going to be some things that those two classes have in common. I believe salamanders and armadillos both have 4 legs. Is that true? If they haven't suffered any sort of grievous injury. So they would all know how to walk. So they would have a method walk. They would have a method eat, because all animals tend to eat. So what we would do is we would not define a method for armadillo called walk and a method for salamander called walk. We would have another class called animal. Animal would know how to walk. All animals know how to walk. When we create a class called armadillo, we would indicate that there was some connection between animal and armadillo. Okay? This by kingdom, animal, armadillo, kingdom, phylum, species. I skipped something in the middle there. Do you play Kingdom Hearts on hard mode? What did you say? Kings play cards on, well, that's okay, because I'm going to play war in a second, so playing cards will come into effect later. If I'd have wanted to be a biologist, I would have gone to biology school. If I had wanted to be an engineer, I would have gone to engineering school. Works for our discipline. It should work for other disciplines. So when you have a class consists of fields, properties, methods, indexers, constructors. And the methods contain code. We write code that executes. Did we skip? We skipped. So I said that our... I said that armadillos are going to know how to walk, and salamanders are going to know how to walk. But really, all animals should know how to walk. Now, that's an important distinction. I said should know how to walk. What I really mean is all animals should be able to walk. So there's another keyword or another vocabulary word I want to introduce to you called an interface. If you are in senior design, you have heard me talk about keeping your interfaces separate over and over and over again. I love the word interface, because if you can define an interface between 2 different components, whether they're software, hardware, personnel, it doesn't matter. If you can define clearly what an interface is, then it doesn't matter how you do a particular task. Okay? If you have a boss who wants a TPS report in 5-column format, it doesn't matter how you make that TPS report. As long as it ends up in 5 columns and you can send it to him, he won't care. Okay? If you are working on a team of engineers and they expect something in metric units, you can do all of your math in imperial units as long as you convert at the end to metric units. Doesn't matter, because the interface is defined clearly. An interface in the concept of object-oriented programming is the idea that you are going to specify what methods should be implemented. Okay, we actually have the ability to define a suggested list of methods. It's called an interface. Almost always we will name the interface I something, so that we know that it's an interface. And when we take this interface and we say, for like the inheritance chart here, we could create an interface for animal that says we should define how to walk. We should define how to speak. And for a dog, they would say bow, and for a cat, they would say meow. So this interface looks like a class, but we don't provide any method bodies. We just say, hey, you need to implement these functions. So a method has executable code associated with it. An interface just has a list of methods that someone else needs to implement. Okay? And we can inherit from interfaces. We say we implement those interfaces. Okay? So we're going to need to get used to the idea of calling things parent and child classes. A parent class is a class that something else inherits from. The child class inherits from a parent class. And what does a child inherit from a parent, biologically speaking? Kingdom Hearts? DNA and genes. These were never my dad's genes, but different kind of genes. What? I have a laser. It's high powered, and I'm not afraid to use it. Okay. So when we do, yeah, go ahead, Tim. Optical power, 1 megawatt. Says MW. No, it's M. It's a small m. Is that how the... See, this is the thing about interfaces, guys. If you define an interface cleanly, like the metric SI unit prefixes, you will never have the problem we just ran into. Huh? Yeah? I brought it all around? Thank you. Okay. So, you're going to hear me use full sentences like this a lot because it's important to get the terminology correct so that you can communicate with other more seasoned engineers as you progress. A derived class, that's a child class, a derived class inherits from a base class or sometimes a parent class. When you have an interface and you have a class that inherits from the interface, it's implementing the interface. So an armadillo implements the animal interface. Or if it's not an interface, if animal is actually a class, then armadillo inherits from animal. Okay? You can actually have, and this is sort of a special one, you can have interfaces that have derived interfaces. So you can have an inheritance tree of just interfaces. Interfaces that inherit from other interfaces that inherit from other interfaces. Like a family tree. It's exactly like a family tree. If you didn't catch on from the parent-child metaphor, family tree is applicable here. It's really the only way to write large-scale code. Question? Okay. Can I put you off a little bit until we have some concrete examples of interfaces, which is sort of an oxymoron because interfaces aren't concrete code. They're just, in the same way that classes can inherit methods from other classes, interfaces can extend the number of things that the implementer would need to implement. Okay, so a child class will implement an interface. That interface might have multiple levels of inheritance so that it starts with one class or class implementation that then it gets expanded multiple times. Okay. Okay. All of these things are super fun buzzwords. It makes your life easier. It makes your code more maintainable, and it makes it easier to reuse existing code in other parts of a project or across different projects. I've mentioned is-a already. When you want to use inheritance, you should always ask yourself, am I using inheritance the right way? You can abuse inheritance and write bad code. It's possible. So you always want to ask yourself, is this a type of relationship where I can use is-a in a sentence? A dog is a animal. Okay. A name is an animal. Maybe? No. No. You are not how much money you have in your bank. You are not your khakis. Come on, tell me you guys have seen that. Oh. So you don't know Batman, and you don't know Tyler Durden. Tyler Durden. Don't talk about that. When you have something that has a relationship, that's a different object-oriented vocabulary word. If something has an attribute, that would be an internal field or property. Okay, it's called aggregation. Okay, so let's talk about a few things. We could write a person class, and what is this kind of diagram called again? I know it's been like a while. It's a ladder. It's a question mark. A UML diagram. We're going to add to what we know about UML diagrams. What I said before, this box, or these three boxes, represent a class. First box, name of the class. Second box, that's your internal state. Third box, methods that that class possesses. We're going to add a few more things to this. That plus sign is indicative of the access type of the field. What are possible access types? Nope. Not get set. Private, public, protected, and internal are access modifiers. The plus means public. A minus means private. Okay. Pound sign means protected. No, not, yes, protected in this language. Protected. So we've got pound sign plus minus. Does everybody know what a pound sign is? This is not lost on this generation. You guys might know it as the octothorpe. No, we don't. No. We don't call it whatever you just said. It's either octothorpe or pound. Minus is private. Thank you for still focusing on the course instead of you're paying a lot of money for this. You're not wrong. Okay, so private, public, and protected is the octothorpe. Hashtag OOP. This arrow, and I'm going to call attention to the fact that it is like a full triangle there. It's not just two lines. It's actually relevant to the UML standard. Line with a triangle at the end of it. That kind of arrow represents inheritance. So, person has a name and address. An employee has a company and a salary. A non-zero. Doubles can be negative, you know. You can have negative salaries. Here's a question. How many fields does an employee have? Think about it. Don't shout it out. Think and raise your hand when you think you know. I'd like more than one person to know before we. How many fields does an employee have? Front row. 4. How many people thought 2? 2. It makes perfect sense, right? There's 1, 2, I can count them. When you have a UML diagram like this, the inheritance says we inherit all of the fields of our parent class. So not only does an employee have a company and a salary, in death, an employee of a company has a name. That's also a callback to our. Meanwhile, a student does not have a salary because you're poor. Okay? Because it's expensive to go here, paying a lot of money. So you would have a negative salary. This is the main point of the diagram, though. That arrow means that you inherit all of the fields of the parent class, in this case, person. Not only do you inherit, the only shown on this diagram are the fields, you inherit all of the methods of a person. So a person might have a method called print address label, would print out your name and your address. An employee would have access to that same method. Okay? Well, let's focus on the C++ or the C# kind of things instead of the Space monkeys, ready to be shot into space for the greater good. Where was it? Okay, that was it. That was it here. The piece that we haven't talked about, again, there are three symbols that we can use in a UML diagram: plus, minus, and octothorpe. Those are relevant because they are access modifiers. What we had before was public and private. Public could be accessed by anything. Private could be accessed only by stuff in this box. If you declare something private in person, you will not be able to access it in employee because it's outside the box. So there's a third protection type that's been useless to us up until now when we start talking about inheritance. And that is protected. So if you do #name, anything outside of this box won't really be able to access it unless there is a path through inheritance to that box. So employee will be able to treat name like a public variable if it's declared protected because it's in the inheritance tree. Okay. But if you're outside the inheritance tree, you won't be able to access it. It'll be like private for anything that's not inheriting. So oftentimes protected is a good option. Okay. You can have inheritance hierarchies that are quite complicated. If you look at the .NET framework, especially if you look at the graphical side of the .NET framework, hierarchies are quite deep. Okay? This is more of a real-world example: games. Class of game. We have two game types. A single-player game is still a game. A multiplayer game is a game, and there's that is a relationship. Minesweeper is a single-player game. Solitaire is a single-player game. They're obviously different. They would have different methods. They would have totally different ways of playing. Okay. Board games are all played on a board, so they all have a board. Might be a different type of board, okay, but they all have a board. So chess and backgammon are both played on a board. Maybe there's another level of inheritance here because chess isn't the only type of game that's played on a chessboard, is it? Checkers is played on a checkerboard, which happens to be identical to a chessboard. So maybe we could have changed the way we did these levels of abstraction. Okay. So in the case of a multiplayer game, there's going to be a winner and a loser. There's going to be a list of players. Okay. In single player games, either we won or we lost, but there's only a single player. We've talked about I/O exceptions and exceptions in general. They follow a hierarchy of inheritance. Okay, so system exception is basically everything inherits from system exception, except for things we create. We create application exceptions. Now, the only thing about inheritance that we have to pay attention to, which is different from something like C++, we can only ever have one arrow going up. This is called single inheritance. Single inheritance is way easier to implement in the back end. Multiple inheritance is possible in some languages. You can inherit from multiple classes, but that becomes a big can of worms. So, C#'s answer to this is you can inherit from one class, but you can implement multiple interfaces. Okay. So if you define an interface, that just says, oh, I'm going to have these functions, have these methods. But the interface doesn't define those methods for you. You have to define how they operate. You just say, okay, I'm going to implement a function called .add, or I'm going to implement a function called walk. That's the interface. We've seen the list, the generic list, before. It implements at least 3 interfaces. It implements something called iList, generic. I collection generic, and I enumerable. Okay, I don't think I'm going to have time to show you the... Actually, you know what? Let's look at the demo of that for a second. Rather than going on. Do I have a mouse? Yes. What I want to do is just go into any old program and make a list of, no, not a generic list, a list of ints. Oh. Here. Turn on screen 0, and then set screen 0 to be projected. Okay. So make a list, and again, because I just walked into any old program, I need to make sure that this is using system collections generic. The reason I wanted to do this, Bob, is I wanted to right-click on it, and it gives me a little bit of information. First off, down here, you probably can't read that. It says T is an int, because this is a generic.list of T. I'm going to right-click on this, and I'm going to say go to definition. Go to definition is going to go into the source code. Ooh. And it's going to bring me to the actual implementation of this class. It's available to us. That is the symbol for inherits from or implements. And it implements I list, I collection, I enumerable, I list, not generic, I collection, not generic, and I enumerable, not generic. It implements all 6 of those things. Okay. None of those are inheritance. I know it's not inheritance because these are all labeled I to start. If I were to go to my generic list and I wanted to create something that could do these things, I could say, okay, I want to implement I list, and it doesn't know what it is, so let's add it in real quick using collections generic of T, like that. Now it's giving me an error message here because I haven't successfully implemented this yet. It's a compiler error to say you're going to implement something and not do it. So again, by the way, I'm hitting Alt-Enter. If I haven't shown this before, Alt-Enter says fix common problems. So I've got 3 options over here that Visual Studio is going to do for me. Implement interface explicitly, or implement through elements. I'm not going to go over implement through elements. I'm going to say implement interface. And you can see it's going to add all this stuff in for me. So I do all this and start scrolling along. And it implements a Boolean, is read-only, a property, which is not implemented. So in order to implement this interface, I list, I need to implement something that says, is this list read-only? I need to implement an indexer, which again right now says not implemented. And there should be a set if I keep scrolling. There's also a set, throw not implemented. Keep going down. Index of, insert into a particular index, remove at index, clear, contains, copy to, remove, get a numerator, which returns I enumerable. Okay, and then this is our method here that we already wrote. So implementing an interface, it's pretty easy to make some boilerplate code. We just ask Visual Studio to do it for us. But we then need to implement each of these. Yes? Because you've got to write them. Okay, we just created the boilerplate function. So we said we want to implement this interface. It said, okay, to implement this interface, you must make these methods. But I don't know how to do it, so you do it. Yes?
Why would you, if you're creating your own class, why would you need like one running?
That's a topic for the next lecture when we start talking about polymorphism. For now, know that it is super useful, I promise. Okay? but we have not gotten there yet. This is going to be a multi-part lecture, okay? This is the real meat of the course. Question?
If you inherited a class instead of an interface, would it have?
It wouldn't be in the code. It would just be available to you.
So you don't have to list it?
No. No, and that sometimes is to your detriment, because if you inherit from something but it's not right in front of you, you might forget it exists. But it does. The methods and the fields exist. Yes, question? Okay, folks, if you are going to leave, I have no problem with that, but there are still some folks asking questions, so just keep it down. You can leave, you can walk out, just do it quietly. You can override, and that's a special keyword, existing methods in the parent class, and that hides their implementation. You can do that, yes. Yes? Yeah, you could, so you could rewrite, a Bob integer class, and you could make addition, do subtraction, and multiplication. You could do modulus. You can do bad things. That's what bad code is. It doesn't do what it's supposed to. But yeah, you could do something like that. Okay, Kyle, was that a question, or did you just have an itchy armpit? Oh, trying to get out. Okay. Any other questions? Yes, Tim. I can't hear you, Tim. I'm going to stop the lecture and we can talk about this.